Hello everyone, my name is Umair, and in this video I shall be presenting our work on characterizing the learning benefits of various adaptive feedback tools designed for compilation errors made by novice programmers. So first, we shall be talking about why compilation errors is an important problem to solve. Then second, we shall be talking about some of the existing adaptive feedback tools that target compilation errors, followed by describing our large-scale user study setup where we deployed these feedback tools in a live setting. And finally, we shall present learning benefits, if any, using a combination of traditional metrics as well as some novel metrics used by us. Compilation errors. So some of you might be wondering, what is the big challenge with compilation errors? Given an incorrect program that fails to compile, the compiler not only reports the exact line number where it encountered the error, it also reports a helpful error message that indicates on how to go about resolving this error. So while for most expert programmers like us, it might be trivial to use this error message and repair the program. However, this is not the case for novice programmers. So imagine the plight of students who are learning their very first programming language in an introductory programming course at a university. Imagine where the student has written such a program where it's quite natural to write two expressions, a plus b and a minus b, in their mathematical form without an asterisk operator and just surrounding them by brackets. Over here, the compiler is talking about functions and pointers to a student who has barely the grasp of what an integer data type is. So while the fix is very trivial, which involves just inserting an asterisk operator in between the two expressions, students typically require human intervention at this point, requiring assistance from instructors or tutors, which is not scalable in a large classroom setting. Recognizing this need, various adaptive feedback tools have been proposed in literature that take the incorrect program which fails to compile as input and produce automated feedback as output. One of the most popular types of feedback proposed in literature is known as repair-based feedback, wherein given an incorrect program that fails to compile, the tool produces the repair of that program as its output. Tracer, which was published in ICSEAT 2018, was the state-of-the-art repair tool during the time of our user study. It could repair about 80% of the incorrect programs in its dataset, achieving a prediction accuracy of 67%, meaning in 67% of the cases, the repair produced by Tracer was exactly the same as the student's own repair. In the three examples listed below, the first example is missing an asterisk operator. The second example, which is a for loop statement specifier, the student has inadvertently used comma in the place of semicolons. And in the third example, the student has forgotten to use a %d format specifier for an integer variable and a comma. Tracer is able to produce correct repairs for all of these examples. The second kind of feedback that we shall be focusing on in our user study is example-based feedback. PEGSER, that was recently published in ASC 2019, is one such tool which takes in an incorrect program as input and generates examples of programs from a different student as feedback. These examples not only suffer from the same mistake as the original program, but also desire the exact same fix. In the examples listed below, TechSet tries to demonstrate through examples the correct usage of an asterisk operator, a for statement specifier, and the format specifier in a printf statement. The hope is that students can learn through analogies or examples the correct syntax on writing a compilable program. Next, I shall be presenting our large-scale user study setup where we deployed these adaptive feedback tools in a live setting. Our user study was carried out at an Introduction to C Programming course at IIT Kanpur, which is a large public university in India. More than 400 students credit this course every semester under the guidance of more than 40 expert human tutors. An important component of this course is 7 weekly labs of 3-hour duration each, where students attempt various programming assignments under the guidance of human TAs. We conducted a randomized controlled trial wherein half of the students from the fall semester of 2017 to 2018 received repair-based feedback from Tracer, while the remaining students received example-based feedback using Texer. Both the set of students received delayed feedback from human tutors in case they were unable to resolve their errors even after 5 minutes. We compared their performance against a baseline group, which is the students from a previous semester without access to any automated feedback tools. These students had the exact same syllabus as our experimental groups and worked on the exact same UI. Students from our experimental and baseline groups across all semesters submitted their assignments through an online web browser-based IDE called Pruter. Pruter has a coding pane in the top right where the students can type in their assignments. In case there is an error, compilation error in their code, then it is flashed in the bottom right of the console pane. In our experimental group semester, the students were shown either repair-based hints or example-based hints in the left side pane. And finally, we report on the results of any learning benefits observed by students with access to feedback tools. Students who had access to repair-based feedback made more than 7,000 compilation errors over the course of 7 weeks and took on average 75 seconds to resolve their errors. In comparison, students who had access to example-based feedback made more than 8,000 errors over the course of 7 weeks and took on an average 78 seconds to resolve their errors. This is significantly more on average than the baseline group of students who received manual feedback from human tutors. Apart from using traditional metrics such as average time taken, we also report on error survival probability curve, which shows a distribution of the time taken. So in this particular graph on the right side, the x-axis shows the time spent by a student on resolving an error. The y-axis shows the probability of the error surviving after having spent t number of seconds. From the chart for labs, we can see that when students have access to either repair or example-based automated feedback tools and having spent t equal to 50 seconds, there is a 7.5% additional chance of them in resolving the error. However, during the exam event, where both kinds of feedback, automated as well as manual, were withdrawn, we observed no variation between the experimental group or the baseline group. One possible explanation for this is that the advantage observed by automated feedback tool group was primarily logistical, wherein it was about faster delivery of feedback rather than conceptual improvement, wherein it was about better understanding of compilation errors and their repairs. And lastly, we report on the performance improvement of the automated feedback tool over human tutored group. In the plot shown on the right, every point refers to a unique compilation error type, with the y-axis denoting its estimated hardness and the x-axis denoting the performance improvement of automated feedback group over human tutored group. From the plot on the right, we can see that the performance advantage of automated feedback group over human tutored group increases with the hardness of the error. In other words, students with access to automated feedback tools have a larger performance improvement for more complex errors and a small performance improvement on simpler errors. In conclusion, we conducted a large-scale randomized controlled trial of more than 480 students, where half of the students received repair-based feedback, while the other half received example-based feedback on encountering compilation errors. Using traditional metrics such as average time taken, we observed that the automated feedback tool group could resolve their errors faster as compared to the human-tutored students. Moreover, using novel metrics such as survival curve analysis and performance improvement analysis, we observed that the performance advantage increases with the complexity or the hardness of the compilation error. Further, this dataset and the analysis scripts have been publicly released on GitHub URL to support further research. And finally, I would like to thank our collaborators, Dr. Sumit Kulwani and Dr. Abhik Roy Chaudhary, for the support in this project.